Patience.
Okay, so hello everyone, and welcome to a new session of the PSE Learn and Share series. Today we have Ben Diamond with us, and he's going to present his latest work on snarks over binary fields. I will let you further introduce the paper. Thank you very much for attending, and please, the floor is yours, Ben.
Okay, well, thank you again for having me. Very glad to be here. Glad to present about Binius, snarks over binary fields. And this is a joint effort by Ulvetana and will be presented by myself, Ben Diamond. Before I get into the substance of the presentation, I'll just say a few introductory words about the landscape that we are stepping into, just to set the stage and also maybe give some background. So you can point to maybe two rough categories that snarks fall into. The first, we can point to elliptic curve-based protocols. Okay, so these tend to be succinct with constant size proofs, constant verification cost, slower for the prover, of course. They tend to have trusted setups and depend on either elliptic curve, discrete log type assumptions, or knowledge of exponent type assumptions. As for aggregation, they support certain kinds of folding, often around cycles of curves, and using homomorphic commitments. The primes, the fields that are used in the arithmetization tend to be large, on the order of 256 bits. They are the scalar fields of elliptic curves. And the bottleneck, of course, is computation. Now, there's a separate rough category that we can call Stark-ish protocols that have become very prominent in the past couple of years. So these tend to have bigger proofs and are more costly to verify, not least because of the size, but also in terms of computation. For the prover, they are much faster. They have a nice recursion story where you can use the same field to arithmetize the verifier that you did to arithmetize the inner proof. So this is so-called native recursion. They support more flexible choice of fields. So smaller fields, let's say 32 or 64 bits for the arithmetization, and then often use extensions during the cryptographic portions. And the bottleneck actually winds up being bandwidth. We can say at Ulvetana, having implemented many things, that what ends up happening is that the sheer cost to move data from a host to a device, let's say an FPGA, turns out to be actually more significant than the actual computational cost. This is essentially because the computation is now so fast that data movement now becomes a bottleneck. Okay, so just holistically, what can we say about the landscape today? We live in a world where proof recursion is practical. It's routinely used in deployed systems. And related to this, the Poseidon hash has become a de facto standard that's used in many systems. This is because in the prime field setting, Poseidon is more arithmetization friendly than than sort of classical hash functions. We also live in a world where lookups are becoming on the margin more viable, more sort of efficient relative to the other components, and are being used more and more. So this will also prove relevant to us because lookups make possible certain things in binary fields, let's say like unsigned integer multiplication, which previously were more of an obstacle than they are now. Okay, so here's an example of a deployed system today due to Polygon. You can see that it involves recursion and batching and various things. So just a couple more remarks about performance of deployed systems. So this is a benchmark of Polygon ZK EVM. We can see that Merkleization represents the dominant cost by some margin. This essentially entails Poseidon hashing a giant matrix column-wise. We note that Poseidon is pretty slow on CPU, maybe 5-fold slower than Ketchak, or maybe a bit more. There is a further phenomenon called embedding overhead, which takes various forms, but one of them is a setting where you have a circuit whose wires in principle could take large values like 64 bits, but which actually in practice during honest proofs end up only having, say, 0 or 1 valued wires. So for example, in Starkey's Ketchak circuit, there are a bunch of columns, something like 2,500. Of those, the vast majority, even during honest proofs, actually only end up having either 0 or 1 valued wires. So all of these things motivate us whether we can design a SNARK system over the smallest possible field, namely F2, the field with just 2 elements. So a brief historical discussion, what happened to binary field Stark? So the original Stark paper, this is due to Ben Sasson, Bentov, Horesh, and Ryabzev 18, was over binary fields. Since then, the topic has sort of disappeared. We can point to a few things that do and don't work. This is a very rough overview, and there's more remarks in our paper, but I can say that there is an NTT analog for binary fields, so-called additive NTT. This is due to Lin Chung Han 14. This definitely works. It's efficient. It's a great technique. Fry does work in binary fields. Actually, the original Fry was written in the setting of binary fields. Other things are much harder to make work, right? So for example, there's the issue of relating rows of the trace in Deep Ali style Starks. In the prime field setting, there's a way to sort of iterate through the trace domain algebraically by multiplying by a multiplicative generator. In the binary field setting, it's not easy to see how you replace that. There is an idea along these lines in HyperPlonk. We will say more about this later. It turns out to be not quite enough on its own. Reed-Solomon codes, including in the binary setting, need to have large alphabets, at least as large as the block length is. So this turns out to be another source of so-called embedding overhead, where even if your message has binary components, the code word might not. So this gives you a blow up in the size of your code word. Maybe you can use Brakedown with a binary code. This turns out to have further issues, and actually we get around this using a so-called packing scheme in our commitment scheme. So we will have time to get to all of these, but that concludes for now the sort of historical and background discussions. So at this point, I'll now sort of pivot forward and sketch what's coming ahead in this talk. Okay, so I'm going to give an overview of tower fields, how they work, why we use them, what the benefits are. I will describe our polynomial commitment scheme. It's a multilinear polynomial commitment scheme that uses Reed-Solomon codes in the binary setting with no embedding overhead, using this so-called packing or block level encoding technique. I'll describe certain so-called virtual polynomial constructions that let you pack and shift and do other things to committed columns. And I'll describe various gadgets that let you do arithmetic operations like addition and multiplication. Okay, so this is crucial because the difficulty of doing these was often viewed as the main obstacle to, or an obstacle towards using binary fields. So we can actually achieve these. Finally, we'll get to the arithmetization of Ketchak, which is a critical sort of component in Ethereum-based applications, and finally some performance benchmarks. Okay, so binary fields, what are they? How do they work? essentially an element of a binary field looks like a string of bits of some length, let's say D, which you can think of as 128, okay? And every such string corresponds uniquely to an element of the relevant binary field, okay? So this is not the case for prime fields. In that setting, you have this kind of wraparound phenomenon. You have so-called non-canonical representations of elements. Don't have that here, okay? Addition is a simple XOR, binary XOR of two elements. Okay, so what about multiplication? And here we need to differentiate between the classical way that binary fields get defined, which involves univariate quotients, and how we do it in towers. So the classical way, essentially what you do is you take a univariate polynomial ring with coefficients in F2, and you quotient that by something irreducible of degree D. So let's say 128. Okay, so the elements of this ring are essentially degree 127 polynomials. These bits then are the coefficients of the relevant polynomials. And to multiply two of these things, we need to multiply binary polynomials modulo this irreducible polynomial. Sorry. Okay, so how does it work? In the tower case, it's quite different. So I'm going to sort of get to this in stages gradually. Essentially, we start in the same way. We take some bit width, which now actually has to be a power of 2. So again, let's just say 128. Okay, and again, each such string of bits is one of our elements of F2 to the 128. But now, and again, addition is XOR. What about multiplication? So the story here is a bit complicated. So let's go through it in steps. What I can say is that we now have a recursive situation where I can split this string of bits in half into two 64-bit chunks. And I'm going to claim that these are elements of F2 to the 64, so the next smaller field down, and that the original thing is indeed sort of made up of these two halves in a sort of not just a formal bit level way, but actually an algebraic way, okay? And this goes on recursively, and we're going to use this to do multiplication and do many other things, okay? So if I have two elements, red and blue, and I want to multiply them, how does it go? Well, very roughly, what I'm going to do is I'm going to split both into 64-bit halves. And then let's say I have a way of multiplying smaller things, okay? So, you know, we still don't know how multiplication works, but at least this is a smaller problem, so we can think recursively. Okay, so if I multiply the two low halves of blue and red, you know, the low half of blue and the higher half of red, and so on and so forth, there are 4 cross terms. And if I can handle those recursively, the claim is that after doing just some further linear amount of additions or extra work, I can then get the answer, okay? And so a couple of remarks. First of all, we'll see soon that this number 4 of sub multiplications can be improved to 3 using techniques related to Karatsuba multiplication. But you know, further, in order to understand what these additional operations are, which is really the substance of it, we need to describe a bit more rigorously what these things are. So just to sketch this as thoroughly but quickly as I can, essentially we want to build up a sequence of fields inductively. Okay, so we start with F2. What we're going to do first is take a univariate quotient, the same thing we usually do, but now of just degree 2, not 128, let's say. And this gives us F4. Okay, so this quotient ring is a field. It's a perfectly good field. So ignoring its internal structure, we can iterate this process. We can write down a further univariate quotient ring whose coefficients come from T1, and quotient that by another polynomial, which I've written down here. And I can keep doing this. So you see what the pattern is. At each level, I quotient by this f iota minus 1 that essentially takes, sorry, this should be, I go to -1, takes the new indeterminate squared, multiplied by the last one, and then add 1, okay? And the claim is that these are irreducible. So they're of degree 2 and irreducible at each stage. So that ensures that these actually are fields of the right structure as desired. Now, stepping further into the future, it was noted, so this was proven by Wiedemann, 1987. It was proven by Fan and Parr that you can actually multiply and do inversion very efficiently in this particular tower. Okay, so this, the complexity turns out to be n to the log base 2 of 3. So this is the Karatsuba complexity. And the idea is essentially something like how regular Karatsuba works, but a sort of recursive version of it. So that's all I'll say at this point, and we can come back. So just a quick, a couple remarks about why we use towers and not the classical approach. So every prior approach to binary fields in SNARKs has used standard univariate quotients. Why not use them in our setting? Well, for a couple of reasons. First of all, we want to support programs or circuits in which other data widths appear. For example, elements of GF2 to the 8, the 8-bit binary field. This shows up in AES and Grostel and various hash functions like that. But moreover, there are other reasons involving the internals of our commitment scheme. So for example, the Reed-Solomon code we use will have an alphabet on the order of F2 to the 16. So we want to be able to work efficiently with these intermediate fields, right? So now it's true that regardless of how I define F2 to the 128, the subfield F2 to the 16 will arise in the big field. The question is, does it arise in a sort of computationally tractable way? If I define it as a univariate quotient, it's just not obvious where F2 to the 16 even lives inside of this big field, right? So in other words, even if I give you an element, if you want to even decide whether it lives in the subfield F2 to the 16 or not, it's not completely obvious. Now, there is some computation you can run that would decide this, but you can't just read it off of the bits. Whereas in our case, the elements of the subfield F2 to the 16 are easily identifiable as the big field elements whose first 16 bits are non-zero, but the rest are 0. This can be determined just from one linear read over the bits, essentially. There are some further subtle problems around packing. So if I want, if I have 16 bits and I want to assemble those into an element of F2 to the 16, how can I do it? Well, in the classical case, I can do this, but the complexity might be something like a matrix mult of size 16 by 128, whereas for us, I can just write down the 16 bits in the first 16 positions. A really kind of non-obvious but really critical point is if I have a small and a large field element, an F2 to 16 and one of these, can I multiply them faster than a general multiplication? So in the classical case, the only thing I can do is embed the small thing into the big field, which has its own cost, by the way, and then just multiplying the big field, right? So you're not exploiting the fact that that one of the operands actually has sort of less information, and then sort of reversing the packing operation. So these all end up being really crucial in the classical univariate quotient approach. They all are costly, and for us, they're all free. Okay, so this is pretty important and will keep showing up throughout the rest of this talk. Okay, so error correcting codes play a crucial role in our work, and there's a ton to say, but the very, very basic thing I can say is that we target Reed-Solomon codes. These have good distance relative to their rate, their MDS. Now, the crucial thing about Reed-Solomon codes is that their alphabet has to be large, at least as large as the block length of the code. So there is just simply is not a binary Reed-Solomon code, for example. The alphabet's going to be something like F2 to the 16. This makes it necessary for us to do things like packing in our polynomial commitment scheme. They are efficiently encodable in the binary setting. So I've already mentioned this result. Okay, so let's charge ahead into the sort of inner core component of our SNARK, which is our multilinear polynomial commitment scheme. And again, yeah, so I'll essentially skip through this. You know, why can't you just do something simple where you just use breakdown over F2? And essentially, there's an embedding overhead problem where if I take a message whose components are just bits and use breakdown, then a priori the code word could have entries in a huge field. So there could be a 128-fold blowup. Even if we use RS. At least the alphabet here is small, but the blowup could still be up to 16-fold. So again, we want that to be 1-fold, no embedding overhead. There's a sort of technical security problem around, can we guarantee that the extractor actually extracts a polynomial over F2 and not something larger, right? So the prover should not be able to get away with pretending to commit to something over F2, but committing actually to a polynomial over a bigger field. Okay, so now I'm going to get into the sort of key packing technique of our polynomial commitment scheme. This is a kind of technically involved strategy that lets us use a plain Reed-Solomon code, but nonetheless not have embedding overhead. And this is described completely in the paper, so I'm just going to give a rough survey, and we can always come back to this. But roughly, here's the story that we start with. The prover has some matrix. These are the coefficients in multilinear Lagrange basis of some polynomial over F2, m by m, let's say. So instead of using breakdown directly, which would stipulate that we encode the rows under some error correcting code, we're going to do a packing thing. Okay, so we're going to proceed in each row, we're going to proceed rightwards and actually bundle chunks of 16 bits into F2 to the 16 elements. Okay, so now I have a new matrix of the same height m, but 1/16 the width, and the entries now are elements of F2 to the 16 instead of bits. Okay, so the question is, can I now pretend that essentially this is the polynomial I started with and apply breakdown now? So this would involve Reed-Solomon encoding these rows, Merkle hashing them, and so on. The answer is not quite. It turns out to be more difficult than this because of the compatibility of the various fields. And this is a kind of technical segment that I'm going to breeze through this. But roughly, there's a naive way of encoding this that turns out to be wrong, right? So this is the sort of value T prime that the prover sends to the verifier. And the problem that we encounter is that it's essentially of the wrong shape. It's too long. Its length is m, whereas our code had message length m over 16 instead, right? So the tempting thing to do where you view F2 to the 128 as a vector space over F2 to the 16 sort of involves segmenting these elements vertically in chunks of 8 and then viewing each slice as a Reed-Solomon message of length m. Now, this turns out to be not what you want. So there's a kind of data layout subtlety that you need to sort of come to terms with that we describe in the paper, where essentially what you want to do is proceed horizontally. You chunk this message T prime into chunks of 16. And how many chunks are there? Of course, m over 16. And then it's a sort of bitwise slices that need to be our Reed-Solomon messages. So it's actually this thing that you want to Reed-Solomon encode, and this is exactly the shape you want. It's a vector of F2 to the 16 elements of length m over 16, exactly as we expected. And you do this 128 times. So this ends up being the right thing to do. This is kind of the key idea of the packing scheme, and this is described in the paper. Going on, I'll now start describing what happens next. So we now assume that we have the ability to commit to multilinear polynomials over F2 and then evaluate them. So what do we do with that? That's what I will describe now. So in the paper, we describe a number of ways of working with these things that we call virtual polynomials. And yeah, so let's get into it. The first is what we call the packing construction. So the idea here is that from the view of the verifier, let's say, this is essentially what's committed to is some long column of bits. And what we describe how to do is that what you might want to work with in practice is a variant of this column where instead of having bit entries, you actually have 64-fold fewer entries, but those elements are elements of F2 to the 64. And when we say a virtual polynomial, what we want is to be able to work with this thing on the right as if it had been explicitly committed to, even when only the thing on the left has actually been explicitly committed to. And we give so in the paper, we give a way to do this that essentially uses sum check, right? So what we find is that if we want to evaluate this polynomial as if it existed at some point, we can write down an expression that involves a sum of this polynomial's entries in over a certain cube, which is sort of exactly the setup that you need to run sum check. So you can evaluate the virtual thing using a sum check over the physical thing. And the sum check is very efficient for the verifier. It would be just something like 6 rounds in the case of a 64-fold packing. We have a further construction called the shift construction, which also ends up being very important in applications. So again, so we start with a raw committed column. We now want to work with a further column, which now has the same shape, so same length, and has F2 elements, but has been shifted circularly, let's say, by some amount of position. So maybe 3, or actually this number can be totally arbitrary. And so this is an important problem. This was sort of posed by HyperPlonk, and we do give a way of doing this for arbitrary offset. The complexity, I'll say a few things in a second. We actually have a further variant, which is a sort of chunk-wise shift, where I can break this thing into chunks of 64 and shift each one individually by, say, 1 position or 5 or just anything. And that shift can be either circular or it can be a simple shift with 0 filling up or down. We have ways of doing this. The complexity, again, is actually independent of the number of positions you shift by. It only depends on the size of this block, which in this case is 64, or in this example was 2 to the L. The complexity for the verifier will be something like log of the block length, so 6 or L or something like that, which is quite good. So why is the shift construction useful? So this is a hint at what's to come. It will be useful in our gadgets for addition, for example, and multiplication, and also in Keccak. Why? Well, it lets us write down constraints that involve columns and shifts of columns, but without committing to those shifts, right? So for example, in the case of Keccak, one thing you want to do is sort of check that the next round state, the main Keccak state, is equal to the output of the last round under some operations. What we can do is sort of zero check a shift of the current state with the output of the last state without separately committing to the shifted current state. So this is very handy for Keccak, and we'll see other examples. I already mentioned this. How do we do it? Just a very rough look into what happens internally. We are able to write down a bivariate polynomial called the shift indicator polynomial, such that when the arguments x and y are in the cube, this thing acts like an indicator for the kind of offset property. Essentially, it returns value 1 if and only if the binary strings x and y differ by an arithmetic addition of O being the offset, modulo the bit width of these binary strings. The key fact that we need to describe in the circuit, paper, is that the circuit of this is only O of B sized. So this is an interesting fact that we go in depth into. So this adapts an idea of SETI, Thaler, and Wabi, where in that case the offset was just 1. Okay, so speeding ahead, I will now say a few things about our gadgets. So let me just pause here and make a remark about lookups, right? So I think a year or two ago, if you had asked somebody, what goes wrong if you try to do a binary field snark? I think many of the responses would have been something like the complexity of your arithmetization will blow up because you now cannot add or multiply natively in your field. And we claim that actually that issue is no longer a problem. Now, first of all, even in the prime field case, you have problems with the range checks, and most protocols actually don't just add 32-bit things, they break into say 8-bit limbs and then natively add those, but you still need to combine them and range check them and things like that. But the other factor is the availability of lookups, which we use in our multiplication. Specifically, we describe a variant of the Lasso lookup in our paper that works for binary fields. Okay, so how can we do arithmetic addition? So what does that mean? So again, we have committed columns x and y, which contain bits, and a further committed column z, let's say. And the thing we want to check is whether, if you proceed through these columns and you segment them into chunks of, say, 64 bits, it should hold for each chunk that the bits of z are the unsigned arithmetic addition of the bits of x and y, and that should hold chunk-wise. Okay, so what we end up doing is committing to a single further auxiliary column, carry out, okay? And what you'll notice here is that carry in is a one-step shift down of carry out, okay? And this is kind of the key fact that we know how carry in should relate to carry out. It should be precisely a shift with zero filling. Okay, so the carry in should be 0 at the first bit of each chunk. And we don't need to explicitly commit to carry in because we have a virtual polynomial for it. And then we now need to write down some very simple constraints. Okay, so z should be the bitwise addition, so over f2, so modulo 2 of x, y, and carry in. And then carry out should be correct, right? So carry out should be 1 if and only if at least 2 of the columns x, y, and carry in are true. And this also you can write down as a simple constraint. Now, interestingly, carry out is on the left-hand side and actually involves carry in, even though carry in is sort of virtually depends on carry out. So this is totally legal. So just 2 constraints and a shift. Okay, so how does multiplication work? So this is sort of a technically involved and very interesting story that I'll describe in a bit of depth. Okay, so we start with x and y, which are really columns, but I've rotated them, and actually these are going to extend horizontally, but I'm zooming into one chunk of, let's say, 32 bits here. Okay, and we want to multiply them. Now, this is going to bring everything together, essentially. This is going to bring together shifting, packing, and also addition in a pretty interesting, and lookups. Okay, so what we do, we're going to split both X and Y into limbs. So you can think of these as being 32 bits and the limbs as being 8 bits each, let's say, okay? And the very rough idea is that we want to run through the schoolbook classical method where each limb by limb product we handle using a lookup, and the rest we handle using additions and things like that, okay? So let's proceed. In the very first step, we're going to have this kind of setup. So I'm gonna do nothing to X. I'm gonna shift it by 0, and I'm gonna what we call saturate. So this is a saturation operator. It's a third virtual polynomial on Y at the 0th position. So this is Y zeros everywhere 4 times, and then X. And if I multiply these two, I get a double width cross term, and then another double width cross term, and so on and so forth. Now, the first key idea is that essentially using one lookup, I can guarantee that these cross terms are correct, okay? That this green thing is actually the unsigned 8-bit product of X0 and Y0, and then this one for X1 and Y0, and so on. Now, there's a key kind of efficiency idea here, which is that how many green polynomials do I need to commit to? Is the answer 4? Well, you can do better, right? So actually, you know, some tricky animation here. So by sliding these things up, the key idea is that if I look at the even cross terms and the odd ones, the evens have no overlaps and the odds have no overlaps. So instead of committing to 4 things or however many limbs I had, I can commit to just 2. It's a constant number of green polynomials per stage of the schoolbook algorithm instead of L. So this is very good for efficiency. Now, let's keep going. Sorry, these got shifted a bit. So keep going here. Now I shift X by 1, so it's 0 here at the first position, and then X0, X1, and X2. I saturate Y at 1, so now it's Y1s everywhere. And again, I do the 3 cross terms. Use another lookup to make sure these are correct. And again, this can be moved up. Keep going through this. Now I shift X by 2, so I have zeros here and here, and I saturate Y at 2. Again, we're doing the elementary school method sort of step by step here, okay? So now I have cross term for X0, Y2 and X1, Y2, another lookup, and then finally in the 3rd position, and a final lookup. So now, putting together all the green things, we had this from the first stage, this from the second, and this and this. And the claim is that by applying the addition gadget to these, we can finally get the actual product. Okay, so what is the complexity of what we just did? If L is the number of limbs per word, we had to do L lookups, 1 per stage. We had to do something like 3 times L commitments. So essentially committing to the green things, and there's one further that it's kind of technical. L0 checks, essentially you're checking whether these the bitwise sort of lifts of these are in agreement with the thing you looked up, and then some additions. Okay, so the key point is that the number of invocations of sub protocols was on the order of L, the number of limbs per word, and not something like L squared. Okay. So final, I guess, thing is that how does Ketchak work? So I don't have too much detail here, but I can say that we have an arithmetization of Ketchak that's very efficient. It essentially commits to 60 raw columns of bits. Each Ketchak state is sort of split vertically. So we have 64 rows per Ketchak state. If you put this all together, we can do one of this sort of core Ketchak F permutation in around 1,500 rows. If you sort of allow a full trace size of 2 to the 28, then you can commit to you can fully prove 164,000 Ketchaks. Okay, so we have some benchmarks. So I guess just dumping the benchmarks here, you can essentially see that we are able to prove in single-threaded and software, we're able to prove a commit to a 2 to the 28 size trace very quickly. So this is something like on the order of a couple orders of magnitude faster than prior works for F2 elements, right? So the key is that our work is indeed exploiting the small coefficient size, whereas these essentially are not. And then we also have benchmarks here for F2 to the 8s. Okay, so I guess that concludes the sort of official content. I have a bunch of sort of auxiliary content if we want to go into further detail into anything. I guess we're running a bit early. Should I open it up to questions now, or how do you all want to proceed?
So, I mean, time is not a concern for us, so you can extend as much as you want. It's more about what you want to do. In regards of questions, we usually leave time at the end of the session for questions. Again, up to you if you want to dive into something else that you think is worth showcasing, or you directly want to jump into Q&A is up to you.
Let's do Q&A and let that drive the.
Sure. Cool. So yeah, let's go ahead and open it up.
So anyone that wants to speak can just unmute himself or herself and ask. Taking profit of the fact that I'm already speaking, I will ask a question. So my question was, well, I have two of them, but I will for now just ask one, which is related to this lookup section that we were looking at now. Are the lookups fixed or dynamic? Because if they are fixed and you are doing operations with 2 to the 16 based elements, you have a table of size 2 to the 32 to cover all of the possible operations that those have, because you have them permuted. So
yeah, so okay, so if I'm understanding you, the comment is about the size of the lookup table, right? So indeed, it's that, so our lim size would be 8, let's say, right? So with a lim size of 8, your table size would be 2 to the 16.
Yeah, right? with size 8, definitely. I thought you were using size 16 here, hence why it looked so big, basically.
So yes, indeed, it's true that if our lim size were 16, our table size would be 2 to the 32, which is probably too big. So I'm in agreement that in practice, you would want a lim size of 8.
I think it's possible that a 2 to the 32 size commitment of 32-bit elements would be practical in some cases.
I think so too.
The key thing being that our commitments are smaller because we're committing smaller sized field elements and we're not paying the embedding overhead. So for example, like we show the proof sizes in the paper for polynomials over F2 up to size 2 to the 36. But that's because they're single bit elements. So but as Ben said, we're sort of predicating the multiplication on the idea of 8-bit limbs right now.
Have you done any further explorations on that, like benchmarks or even estimations on whether would it be worth it, or which are the cases on which you foresee that it's worth it to go towards the direction?
You mean to the direction of increasing the lim size?
Exactly, yeah, to having a table of 2 to the 32, which is probably the theoretical maximum that we can aim for nowadays.
Yeah, I don't have anything concrete to say about that. It would depend on application. So I imagine if you're doing snarks to prove elliptic curve operations and doing big field arithmetic where like multiplication is a heavy operator, then you might want to do that. It sort of depends on the application. As Ben noted, like our Ketchak circuit and all of the hash functions that we're targeting make no use of lookups right now. So yeah, I don't have anything more.
Yeah, fair enough. That makes sense.
Do you have benchmark of Ketchak?
Not yet. We're working on that. We have a thorough description of the arithmetization in the paper, which is more complete than what's in the slide, but we're working on a full snark to prove the Ketchak circuit, and we'll hope to have, you know, results on that in a month or two.
Right. So we can tell you exactly how many columns, what shape the columns, and then what, you know, zero checks and things you need to do, but we just haven't implemented it yet.
Yeah, I can also say that we did run some benchmarks on looking at our sum check efficiency, and like basically did benchmarks of like if we were to do these sum check operations for, you know, this degree of polynomials that we need and for the number of multiplications, and came up with an estimate that we could do 5,000 Ketchak Fs per second per core. And that would be basically our target right now, taking into account the cost to do the polynomial commitments to F2 elements and the cost to do the sum checks for a 2 to the 28 size trace.
In what hardware is that? Because that is almost faster than running it natively without proving anything in your machine.
That was on the well, that was single threaded. I guess we should double check that, but that's the estimate we came up with. That was on AWS GFN or like a C7i, you know, probably metal or 32x large instance, which has an Intel CPU. We're using the Intel CPUs because they have particular instruction sets that make the binary field arithmetic efficient.
Wow. Okay. That's awesome. I will read some questions that I see in the chat. Wyatt is asking, what is the space / memory efficiency versus things like Fry?
Yeah, it depends on the application. So our major claim here is that for many circuits of interest, you actually are committing to elements that are much smaller than the field required. So first, it depends on the application, but like for things like these hasher circuits where you're doing a lot of bitwise operations, the memory requirements are, we could like sort of get a theoretical up to 32x improvement because we're only committing, you know, the bits themselves, and basically where you pay for this is in the sum check protocol, but the memory requirements, it actually doesn't blow up the memory requirements because there's basically some techniques for doing sum checks over small fields that we're able to leverage. So that actually makes it, you know, more of a compute bounded computation. And sorry, you asked about memory requirements versus what was the
Compared to Fry, right? Memory requirements.
Yeah.
Fry.
Oh, sorry. And then are you asking about Fry over binary fields or Fry?
It's quite noisy where I am right now, but I'm curious in general. You mentioned very early on in the conversation that there was hardware limitations. Like if you tried to move from CPU to custom hardware, it would cause issues for you. So I'm just thinking in terms of space efficiency, does it make it much easier for you to have special hardware?
Sorry, that was hard to hear.
Yeah, the mic doesn't sound really good. Wyatt, maybe you can write it down.
Yeah, I think essentially the answer, yeah, I guess by Fry, I'll interpret you to mean something like, you know, Deep Ali, right? Which uses Fry as a subroutine. I think it essentially comes down to what you're comparing to. Are you comparing to Fry, where your circuit has arbitrary 32-bit values, or, you know, Fry Deep Ali, where your circuit has 1-bit values? In the latter case, we're essentially going to do better by something like a factor of 32, which we think is the more practically relevant comparison, right?
Another thing to note that maybe wasn't explicit is there's a even in the binary field setting, one of the really nice things about Brakedown is that we can shape our matrices so that for practical sizes, we can have block lengths of at most 2 to the 16, which lets us use the 16-bit field, versus if you're doing Fry, it would make more sense to, you're probably committing or you're probably encoding with a block length that's greater than 2 to the 16, because it depends how much you're batching, but that would sort of make sense. And so in order to just do the Reed-Solomon encoding itself, you would need to use multiplications over the 32-bit field, which are, you know, scale something like, I mean, I have the exact numbers somewhere, but
more than double the cost of
yeah,
an
more
F2
than
bit
double the
16.
cost. How much of a speed up do we achieve using Intel GFNI? It's significant. That said, we've put pretty much all of our CPU optimization efforts into the implementation with the GFNI instructions. So it's an interesting question. We have we've developed like algorithms for kind of essentially doing vectorized field mults, which recursively call more vectorized field mults. So if you know, we actually, maybe Ben, do you want to go, do you have anything deeper on like how to do multiplication or?
Slide wise,
So
not
I guess
exactly, but
if
I
you
can
want to
just say,
scroll back to the the field mult
yeah,
slide.
sure.
I mean, it doesn't need to be slide format for the recording or anything. You can just show whatever you want, guys. Whatever is easier for you to show it.
I guess what I'm trying to say is that if you do this recursive decomposition sort of as scalars, like you know, Ben showed a version where you have to do 4 recursive multiplications, and then there's actually another version where you only do 3 recursive multiplications and 1 recursive like multiplication by a special constant. If you sort of do that naively non-vectorized, it's more expensive, but we also developed an algorithm that essentially can do vectorized multiplication of field elements, which will recursively reduce to a vectorized multiplication of the subfield elements. And this is all based on the idea that like you have a string of bits, let's say it's a 32 bits, and you can sort of cast that into either an F2 to the 32 element or a 2 wide vector of F2 to the 16 elements, or a 4 wide vector of F2 to the 8 elements, or so on.
Maybe shot at this question about the code word has to work over. Maybe Nicholas, if you can explain the question.
No, it was just like in your explanation, you were saying the code word is F2 to 16. And is there any reason for this, or it's just like variable, or it's just for the sake of explanation?
So, okay, I'm not sure I understand, but one fact is that the alphabet of Reed-Solomon, in our case, has to be at least F2 to the 16 or larger. So the elements of your code word, maybe the comment was if you start with a message whose entries are bits and you read Solomon encode that, then the entries of the code word will be elements of F2 to the 16. Is that the remark?
Right. Yeah.
So the reason that is essentially comes down to how Reed-Solomon works, right? So the alphabet is going to be F2 to the 16. It's like mathematically, essentially what you're doing is multiplying this message by a matrix whose entries are in F2 to the 16. And after you do that, the vector that comes out will have larger entries. So this is essentially a fact about the alphabet size of Reed-Solomon codes.
Maybe just to say it slightly different and to explain why we use the term embedding overhead. Like if you wanted to use Fry, for example, what you would do with you know bit entries, so your elements of your encoded of the polynomial you're trying to commit are bits 0 or 1, you would embed them as elements of F2 to the 16, and that would effectively be a padding with 15 more bits. And then you would multiply by a generator matrix, which has elements from F2 to the 16. So that's where we get the term embedding overhead, and the purpose of our polynomial commitment scheme is to be more clever than that.
I have one more question related to the packing construction, specifically on how are you performing the sum check for elements on the 2 to the 64 range on the 2 to the 64 field, when indeed you are not in that, like this kind of, I know you're not emulating,
This is
but
the packing vertical polynomial.
Yes.
yeah,
Yeah, you're referring to this setting. How do you perform the sum check here?
yeah, exactly.
Okay, so maybe now actually I can pull up the other slides very quickly. Am I still sharing? Do you all see this?
Yeah, we can see it.
Do. Okay. Okay, so essentially this is the relevant content, right? But just to say it in words, the polynomial here actually never really exists. It's actually virtual, right? So rather, it's this polynomial that exists, and the thing that you sum check is a certain sum involving this polynomial, right? So it's actually a polynomial whose entries live in F2, or yeah, not quite. It's a product of your original F2 polynomial with this beta. Okay, so this beta is a sort of special basis of F2 to the 64 over F2. So this ultimately turns into the thing that you need to sum check. Now, there's a further algorithmic question, which is how do you efficiently sum check something whose entries live in a subfield? And that's a sort of a further topic, but maybe I can ask you which aspect you would like to see more info on.
This is really interesting, and also at the same time, the reply that you gave me was pretty clear. I'm just wondering, how was this beta derived? Like, what process do you need to follow such that you end up with a beta that is good for you to perform then the sum check over?
Okay, so the beta, I skipped this material at the beginning, but the beta is an intrinsic sort of part of the tower field. The beta is a special a sequence of elements of F2 to the 64, which give you a basis over F2 of F2 to the 64. So specifically, these are essentially the monomials, the possible multilinear monomials. Any element of F2 to the 64 looks like a sum of these. So these are constants, essentially global constants that depend only on the tower field and exist sort of forever. And the key observation that makes packing work is that in order to write down an F2 to the 64, on the level of bits, I just concatenate 64 bits. But that concatenation actually is algebraically meaningful. It actually corresponds to a linear combination where the coefficients are my 64 bits, and the things you're combining are these betas that are sort of vectors. They're elements of the big field which form a basis. So it's this algebraic expression that actually captures the packed thing. And then the further observation you make is that this expression is itself a sum, and so is amenable to the sum check. And that's kind of, so if you write down this internal thing, then sum checking this turns out to be enough. Where here beta hat is a kind of a weird trick. It's actually taking these betas, which are just an array of elements, but viewing them as the evaluations of some multilinear and then taking its multilinear extension. So we're viewing beta now in kind of multiple ways. On the one hand, it's a basis of this field over F2, but it's also the evaluations of a multilinear, which we call beta hat. And, you know, beta hat is sort of efficient to evaluate, and this lets the sum check work.
And just two more comments on that. Beta actually has like a very simple description. Like I can tell you that all the beta elements are Hamming weight 1, and the, you know, depending on the indexing, the 1 is at a very particular place, and that's just an artifact of like the particular tower construction we use. And then the other thing to just observe here is that the sum check that we're doing is actually a very small sum check. It's over like 64 elements. It's not like you're adding another big sum check instance or something, which we would be more wary of.
So the complexity of the sum check depends only on the block size that you're packing, not on the column size. So in this case, it would be something like 6 rounds, not, you know, L rounds or something like that, right?
That makes sense. That makes sense. Thank you.
Yeah.
Quick questions still on this slide, maybe. The sum check is, or the polynomial that you're sum checking over, this is of degree 2, right? So the t is degree 1 and beta is degree 1. Okay, thanks.
Yeah.
So, well, degree, okay, so degree 2 in what? In capital X, this is, yeah, it is, yes, absolutely.
Thanks.
Any other questions that anyone has? Okay, so I think we can wrap it up here. Is there any last thing that you guys, Jim, want to mention?
I should have a useful links slide. Maybe I can just jump to that if I still have it. Sorry, give me just a second.
Yeah, I guess just to say, like, we have we're working on an open source software implementation of this called Binius. You know, developing that, like, you know, things are getting pushed in real time. We're working towards full snarks for various hashers of interest, including Ketchak, Grostel, and SHA-2. And certainly when we get those done, we'll be publishing the benchmarks on that, and I think that'll answer a lot of people's questions about concrete performance. There's more details in the paper, and we'd love if you guys have any feedback that you can share with us on this presentation. You know, we'd love to hear it, because we want to do our best to educate the community about our work. So
Yep, and I'll say that you know, thanks again to the audience, and I welcome any questions or comments by email. So anybody either here now or watching in the future, feel free to email me with questions.
Oh, and last plug, we're actively hiring cryptography engineers to help us build this. We think it's going to be the best snark in the industry, so it's an exciting time to join us. And if anyone's keen to do that, you can reach out to me directly by email. I'm Jimpo, JIMPO @Ulvatana.io, or if you have referrals. Cool, thank you, everyone.
I'll add the emails in the description of the video so that you can basically read them.
Great.
Guys, thank you very much for doing this presentation and spending time with us. It has been amazing and really insightful. So yeah, once again, show our appreciation for you coming here today, and have a nice day, everyone. Enjoy the rest of the day. Cheers.
Thank you all.